Let's do a quick little review on kinetic energy. Suppose I did work on this thing and I made it speed up, and I wanted to know, like right here, it was moving with some speed, and I don't have a work meter. I don't even know what force I exerted, but I still want to know the kinetic energy of this mouse as it was screaming across the screen. What would I do? Do you remember? K, the kinetic energy, we have a formula, 1/2 mv squared. All right, so all I would need is I would need to know the mass of my mouse, and I would need to be able to get the speed, and that's all there is to it. I didn't have to know the amount of work that was done. I know how much work that was done but I didn't notice there's no talk about, well, how much force, through what distance did you act. It's all based on the mass of the mouse and how fast it was going. I want to do the same thing with spring energy. I'm not talking about making this spring move. That has kinetic energy. I mean, if I come across a spring and it has a certain spring constant, and I know, and basically I see that, oh, you have been compressed 10 centimeters, I want to know how much energy is stored in that spring. Okay, that is our goal here. Okay, so let's get to it. So let's start out with work. Okay, so we want to quantify spring energy. That is our goal. Let's see, am I lined up here? Okay, well, work is energy transfer, so basically that's going to equal the energy in our spring, technically delta, but if we start out with it not squished, like we're starting here and it goes here, then I don't need to worry about that. Okay. So all I need to do is say, okay, so the spring energy is going to equal the work, which is going to equal F times D. And I realize, in this case, because somebody had to exert a force like that, and the distance through which the force acted was that, and that is the same thing as the amount of squish or the amount of stretch. And I go, well, that's easy, except that's wrong. Okay, or that's a huge problem because that F is not constant. Okay, so how do we deal with the fact that this force, as I start to pull on it, this force initially, it's a pretty small force, but then it gets bigger and bigger and bigger. So how do we deal with a variable force? And it's really pretty simple. Let's go back to impulse versus and momentum. Okay, just because it works the same way, and you've seen this before in a different context. All right, so basically, if I have a force and it acts over time, this is impulse now, just going back, revisiting. If I have a force and it does some crazy thing like this, and it acts over time, is how would I get the impulse? Impulse, J, is F times T, but that's not true. Well, this either has to be constant or the average of the force. But if I look at a graph of force versus time now, not distance because we're talking about impulse, how did I get the impulse? Do you guys remember? Yes, I hear you. Yes, you're all shouting. Yes. It is the area under the curve. Area under the curve is impulse. So that's how we're going to deal with our problem with our force of our spring. And the work you have to do in compressing a spring is your force is going to get bigger and bigger and bigger and bigger and bigger the more you compress it, or conversely, it's going to get bigger and bigger and bigger and bigger. So we can't simply just take that, okay? But it's not that hard a problem. Okay, let's go back to Hooke's law. A graph of spring force versus stretch. Could be squish, we're going to do stretch. So we're going to imagine making this thing get longer. And this is an ideal spring, as they always will be for us, unless you're specifically told, hey, it's not an ideal spring. And we would get a graph that would look like this. And let's suppose that you stretched it by X amount. This is just, okay, This is the amount by which it's been stretched. Okay, well, how much work did you do on the spring? And guess what? If impulse is the area under the curve of a force versus time graph, what do you think the area of a spring for, well, just a force versus distance graph tell us? And it is the area. Okay, so the work done equals the area under the curve. So let's just go through that, because there's your answer. So the work you do in compressing a spring is going to be the area under the spring force versus stretch or squish graph. Okay, well, I see a triangle. So the work you do, and this is going to be equal to the energy in our spring. This is why we're pursuing this. Okay, so I see a triangle. So that's going to be 1/2 base times height, where this is the base, this is our B, and this is our height. Okay, well, the base is easy. That's just the amount by which you have stretched your spring or squished. Okay, so this is going to be X. Now, what is the height? Sorry. Why did I put an X there? That's H. Should be H. It's very confusing. Sorry about that. H. Well, the H is going to, if we come over here, the H is going to be equal to the spring force, like when it's at this value here. So that's going to be spring force at X amount of stretch. Well, what is this? What is this guy? How do I quantify the spring force of a spring when it's been stretched by X amount? Well, that's going to be 1/2 kx. So we're just going to make that substitution, and we get work done on a spring in making it stretch or squish is 1/2 x times, no, sorry, it's just kx. Sorry, I'm not going to go back and remake this. Sorry, I've got this 1/2 on my brain here. Kx, that's the spring force. And that's going to be kx. Sorry about that. So all I do is simplify it. So there's the work you do in stretching a spring or squishing is 1/2 kx squared, where k is, I'm running out of room here, but that's the spring constant. That's the measure of the stiffness in typically newtons per meter, but it could be newtons per centimeter. But in this case, it needs to always be a newton per meter because we're getting into joules, etc. And this is the amount of stretch or squish. Okay? That's it. That's how we quantify the energy in the spring, because that's how much work you do. So to summarize and wrap this up, we can quantify the energy in a spring by knowing two things. What is the spring constant? Well, the 1/2 is going to be there, but if I need to know the spring constant of my spring. And then I need to know one other piece of information. I need to know by how much in meters has this thing been squished or stretched. Okay? Spring energy, electric potential energy, is 1/2 kx squared. It is a scalar. And there you go. That's how you quantify the energy in a spring.